Okay.
Right.
Okay, where are we? 12:45. So we started at 20. Okay, we're halfway in. Okay, so just to repeat, so just what we just had was we basically discussed the fact that we expect capacitance to be a straight line like this with a non-zero y-intercept. And we worked through the work here, and indeed we found that there is a minimum value, which should be the y-intercept. That's this value right here. This is the value for x equals s. And in between it increases linearly, so it matches up there, okay? And I'll take a picture of this. And I have a phone. And my phone is here. Okay. And I'll take a picture and I will post that in a little while. Actually, I'll post it right now. That's a good idea. I think that, yeah. So WhatsApp, I'm posting these on WhatsApp, and then Christopher, I will forward this to you later. Let's do it this way. I'll do it right in WhatsApp. That's probably better. So there we go. Okay, there we go. Good. So I'm going to leave the equation there and erase the stuff we have underneath where we discussed how this makes sense. Good. And come back to the idea that we just discussed. The idea we just discussed was that this is a straight line with a y-intercept that's non-zero. So let's actually make sense of that, because here we have what is x, and x in this case actually is x, and then over here we have what we call y. Now the format we have here is a little bit awkward, as you can tell, because they have things kind of mushed together. And just as a reminder that we're supposed to have, well, not a reminder, I'm not going to remind you about this, but we're actually going to take this equation and kind of reshape it to make sense of it, expressing it like this, because
Exactly. What's m in this situation?
exactly, that's what I'm saying. Okay, so that's the way we want to have it, but it doesn't look like it's actually in that shape. Do you guys agree?
Yeah.
Okay, so let's actually take this equation and multiply this thing out over here. And let's see what we have. So we have here c is equal to epsilon naught s squared divided by d. That's the first part, right? And then we have plus, and I'm going to take the second thing and multiply it out as well, right? And we're going to have here epsilon naught s over d times k minus 1, okay, times x. Do you guys concur? I mean, I just flipped this a little bit to put the x at the end. And the reason for that being that x is x. Agreed? And c, well, that's y. There we go. Ooh, now we're cooking with oil. I'm getting excited. I'm getting geeked out. This is good times, okay? Now we have a factor in front of x, and that, of course, is m, the slope. Okay. And then, of course, here, voila, les haricots verts, we have b, the y-intercept. You guys agree?
Yeah.
Okay. And unfortunately for you guys, pretty much only like, I think like 2 people were able to do that. And you probably know who that is. So yeah. So I was assuming this would go better, but it didn't. So that was a bummer. But now that we've talked about it, do you feel a little bit more confident understanding how that graph now makes sense?
Yeah.
Good. So now that we have written it out like that, basically, we can say, okay, well, this thing here, right here, right? That's the y-intercept. And if we look at our graph, right, we have that value given to us. So that's kind of how they did have this problem almost exactly like this on an actual AP Physics C, E&M exam, but they asked people to do the graph and then find the slope. And I was like, I can't ask you to do that. I'll just do the graph, give you guys the slope and the y-intercept, and everything would be great. And then it wasn't, but okay. But now you guys know how you would be doing it. So you have the slope here, and you have the y-intercept. Y-intercept is 0.836 nanofarads. Okay, so this is 0.836 nanofarads right here for the y-intercept. And then for the slope, we have 9.04 nanofarads per meter, and that's this thing, 9.04 nanofarads per meter. Am I still on the screen? I am, and that will be the value for this thing. And just to clarify that, I'll put a nice black circle around it to make sure that's clear that that's what that is. And over here, the y-intercept, that's this value, is equal to this. And just checking through what we know. So in the question, we're doing like question B, C, D here right now, okay? So we'll come back to question A, although I think, yeah, I don't want to make you feel bad by telling you that that was the easiest part, but anyway, we'll get back to that in just a second. But okay, so let's just finish this part. This is really B, C, D, and then we'll come back and do A. Okay, so if we look at this, this is equal to this, and we know S, right? And we know D, those are given. So this equation should be solvable for epsilon 0, experimental value for epsilon naught, okay? So you can solve this for epsilon naught, and I think I'm not gonna go through the process. I'll just tell you that you can do that, okay? And the solution shows how to do that. Now, if you look at the other one, the other equation is a little bit more complicated, but here you have this value here for this whole thing, and we know S, we know D, and there's a little bit of trickiness here because then you have epsilon 0, like, wait, do we know epsilon 0 or not? Because just a second ago, you asked us to find it. That's why in the problem, I actually told you guys to use the accepted value for epsilon 0. So we're going to consider this known, and obviously you know what 1 is. It's a number. That leaves then only K in this equation, and you can solve this equation for K and find K. Okay?
Yeah.
Does that make sense? Cool. Now, that takes care of parts B and C. And now let's come to part D. And you guys, as a group, super sucked at that one too. And I think it's okay. And I'm glad we're having this chat now. So I want to look at that because you guys tend to be really bad at questions regarding errors and those kind of things. So let's just look at the question and read through it carefully. So it says, assume the value found in part C is higher than the accepted value for the permittivity constant. State one possible physical reason for this error and explain how it could have caused this error. Okay, so what do we have here? We have here two conditions that you need to meet. What are the two conditions you need to meet?
That it's a physical reason.
Good. And?
That it would make the permittivity constant higher.
Then it's really 3 reasons. And then the other thing is that, and I'm actually less worried about that because honestly, if you come up with a physical reason that somehow affects the situation and then explain it properly, that's the other aspect. So you have to explain how is this connected? Some physics. We want to see physics knowledge. Okay, so the first thing, and this is the one that most of you completely got wiped out on, is it has to be a physical reason. Okay, so that wouldn't be, even though hopefully your lab partner is a physical object, saying my lab partner is a moron, didn't use a ruler right, and measured the distances incorrectly, would not qualify as a physical reason, right? Make sense? So, and a lot of your answers were in that directions. We might have mismeasured the D, we might have mismeasured the S might have been mismeasured, blah, 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 or we didn't properly insert the dielectric and therefore blah, 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 blah. It's not really a physical reason. So basically, it's asking for what assumption are we making? And there's a physical reason why this is actually not true, okay? And I gave 3 examples, but don't look at that right now because I don't want you reading it back to me. Well, for me, if you're already looking at it, that's fine. But let's think about the situation and let's think about the assumptions we made to make this work, right? So when we did this, we assumed, for example, that this capacitor is 2 capacitors, right? And really the 2 capacitors, if you think about it, are this one, the black capacitor, just this thing right here. Make sense? The black capacitor. And then we had a purple capacitor over here. Make sense? And we said that's the only thing we need to consider. But is there a physical reason in this situation? Let's look at the physical reason that we're like, what are we ignoring here? So what are some of the things we're ignoring that might affect this actually? Suggestion? Me leaning back's a hint. What are we ignoring that I'm covering up now, but that's actually still there?
Oh, the external part of the dielectric.
There's still some dielectric over here. Now, maybe that somehow affects our situation, right? Because our electric field, we oftentimes think about it, right, as limiting itself to just being between the plates. But is it actually limited to between the plates?
No, you have edge effect.
There are edge effects. So there would be some electric field here. And of course, that electric field here would be affected by the dielectric actually being there, right? So maybe this could have a small effect, the fact that we have some dielectric over here, and that actually we're ignoring that aspect because we are not thinking about the edge effects, okay? And the fact that there's dielectric sitting right next to it could affect it. It's a physical reason. Dielectric would have a tendency to make it easier for electric field to be there, right? And therefore, this could cause that error in measurement. Make sense? Okay, so that would be one example that you would come up with. And obviously, there's edge effects over here as well. Makes sense? Okay, but what's the other thing we're ignoring? We're looking right now here, and we're saying this capacitor has in between the plates what?
Air.
Air. And we're treating air as what in this problem?
A dielectric with K equals 1.
K equals 1. Now, is the K for air actually 1?
It's probably very close to it, but a bit less.
It's very close because it's not a vacuum, right? Epsilon naught is for not, for 0, for none, for vacuum, okay? So this one right here, you could say epsilon is actually greater than epsilon naught. Just a little bit, yeah? Maybe not a lot, but it's a little bigger, okay? So that would mean we have a physical reason to say there's a problem there because we've got a material in between there which is actually not vacuum, and that could change our results. So both these and these could actually effectively increase the permittivity of the whole device, okay, and therefore effectively increase the capacitance just a little bit than what we're thinking it is, and that would affect our result. Okay.
And what was the third reason?
The third reason, and it has to do actually, and this is one of those things where like you're in the process of measuring this, okay, how did we ever get to actually measuring the capacitance? They used a really awkward kind of approach to doing that. We're back to part A. What did they do to get there? They closed the switch and they measured the time it took to fill it halfway, which is like really? That's the way we're going to do it? Okay, all right. Somehow it's connected to capacitance. It is, but in that, we're relying that the voltage here, right, is actually the same as the voltage over here. And in that process, current is flowing, right? So as we're measuring the voltage here and recording it, there's still current flowing over here onto the capacitor. And it's flowing through wires. And what assumption are we making about the wires?
That they have no resistance.
They have no resistance, but they actually do have some resistance. So there's a physical reason to believe that the voltage we're measuring, and we think it's the voltage over here, is actually slightly larger than the voltage across the capacitor plate.
Mm-hmm.
Makes sense? So we think that it has reached half load, the half of 3 volts, at a point when it actually hasn't yet, because it will max out at 6 volts still, right? Because eventually this voltage over here will be the same over here, because when there is no current flowing, then these wires do not drop any voltage, but that's later. Okay, so eventually we'll reach 6 volts, but when we think 3 volts have been reached, 3 volts have not quite been reached over here. So we're basically under measuring the half time, the time 1/2, in order to get to 3 volts. And if you look at the expression that you should have been able to derive for the capacitance, then you'll see that your capacitance that you therefore have determined is slightly too small. The actual capacitance is slightly bigger. And that's, again, the same idea as with these other 2 effects. The side of the dielectric over here and the fact that this is not air tends to actually mean we have more capacitance than we think there is. And the same thing is true with the voltage measurement here, meaning those wires actually drop a little voltage. Therefore, the actual capacitance is larger than we think it is. So all 3 of those answers would work. And again, I wasn't in the room, so I don't know, but they had one of those as an example. They only had the wires. I like the other 2 answers too. They're all physical reasons, and they explained physics. You know, I mean, obviously it's physics, but you're showing your physics knowledge, and you're connecting it to capacitance and why it might imply that your measurements are off. I think they're all good. All of these effects are rather small, okay? I think. So I think they wouldn't make a huge difference, but they just wanted you to talk about the physics. So we did. So those are the 3 things. I hope those 3 things make more sense now. We can take just,
It does,
yeah, go ahead.
but why wouldn't things like the thickness of the dielectric, or saying, you know, it's actually greater
Sure.
or less than?
That is not a physical reason. That's a measurement error. That's like you making a mistake. Because
Right,
so these numbers here, right, 0.001 meters, we're saying those are right. So if you didn't measure this right, or the thickness of the dielectric is actually different, or the plate width is actually not 0.3 meters, that's not a physical reason. That's a measurement error that you introduced based on how you measured the stuff.
So I can't imply that the company like said they have a 500 ohm resistor, but it's actually less. I
That's
can't
not
do
a
that.
physical reason. That is a
Okay.
measurement error that's brought into. So if the question had asked how might measurement error have caused this number to be different, then you could talk about the voltmeter is actually probably has some imprecision. Your meter stick, well, you can't use a meter stick for this, but your micrometer or whatever you're using here has some imprecision. The ruler we have has imprecision. Their measurement error would introduce it, but it could introduce either way. That's the other thing too, that there's no particular reason why you would think that any of those measurements would affect it in one specific way, whereas the physical reasons that we discussed, all 3 of those have the specific connection to underestimating the capacitance. So that's that. And the last thing that we were kind of towards the end of the office hour. So I didn't want to address part A. Part A was a little sneaky, and the reason I liked the sneakiness was because I can see them doing something like this, because we talked a lot about tau, the time constant, But here they're not asking for tau. They're asking for the time to get to a half of the voltage. So the difference being that tau, because it's an exponential function, has like, I don't know what it is. It's like e to the minus tau or something like that is equal to whatever. Anyway, I'm sorry, now I'm getting confused. But anyway, the point is it ends up being like 69.3% or something like that. It is not half. Okay, and that's the trick here. So when you do that part, you need to make sure you go to a half. I'll just take a quick picture of this and then I'll erase it. Wait a minute. No, I don't have a clean board over there. All right, let's just go this way. So I'm going to just take this picture of the whole thing. There we go. There we go. Send that. And let's go and erase this.
So this wasn't asking for the time constant, but the half-life?
It was not asking for the time constant. It was asking specifically for the time that it would take to get to, how is the half time related to the capacitance. And the reason why this was not just your physics teacher / question writer hating you is because in the lab, that would make a lot of sense, right? To measure T1/2, because you could easily imagine setting this up. It's like, oh, dude, we got 6 volts here. We'll just see how long it takes to get to 3, right? Okay. That's easy to measure. But to coming to 69.3%, you're like, okay, 6 times 0.693, and then, oh, okay. No, the number is like a wacky number. It's hard to actually measure, but going to half would make a lot of sense. So if we look at the equation we had V across the capacitor equals V max, and then we have 1 minus E to the minus T over RC. There we go. So if we're looking for the half voltage, we're just looking for 3 volts equals 6 volts times 1 minus that. Okay? And then this is T1/2 here. I'm going to actually clarify that. So this is T1/2 at this point. Okay, and now we know everything in here besides this, so we can solve it. And if you do solve it, then you end up with that the capacitance is equal to, and I'll just write it out because we're out of time, but I think that's, solving it is relatively straightforward, and it's also in the on the sheet. There we go. Oopsie, it's up. Here we go. So that's what you get. So you basically rearrange, got to take the logarithm, natural log to get rid of the exponential there. And if you do that, you're all set and you end up with this answer, which is slightly different than tau. So tau is related to this, right? Just a reminder that in that term, C would be tau divided by R. So yeah, it's a similar expression, but there's a number correction factor. That's actually where my 69.3 comes from. That's actually not the correct number for what tau means, but okay, whatever. So there's just a correction of a time there. Okay, and hang on a second. I lost a minus sign or something. Did I? No, it's good. This way is right. If you write it with ln1/2, it will be minus, and then you have ln1/2 down there. Those are all acceptable. But I have all the acceptable answers on the sheet, and there you go. Okay, you feeling better about question 1 and or life?
A little bit.
Little bit. Okay. Just a word of encouragement. Just keep. This is hard stuff. We're learning things that are difficult. And just keep doing what you can and try to get better, and every little bit helps. So don't get discouraged, and just when you get to the test, try to do what you can. They have clearly stated that on the test there's going to be a high ceiling. There's going to be a possibility of students to show their understanding, and that might include that they can't complete all parts. And don't get discouraged if it's like, how am I supposed to do this in 15 minutes? So again, the idea is that maybe you can do parts A, C, and D, and B and E you just either can't do because you don't know that stuff, or you don't have time to get to it. But they just want to give opportunities for students to show that they understand physics, and then basically they will factor that in the curve later on. They just want to have many places where you guys can actually show that you know something. So as long as you can pick up points somewhere, obviously if you get a 0 on the question, that's not going to be good. But if you can pick up parts A and D, that might be enough to get you just across where you need to go.
Okay.
Okay, so don't be
Thank you.
freaked out if you can't do all the parts. I mean, same thing on the actual AP exam again. You're looking at, I said 50%. I think 50% you're good. If you get 50%, you're getting a 5, I think.
Okay.
So you need half the points. Okay, and for a 3 or 4, you might be looking, what did I say, 55, 45, 35. It might be 50, 40, 30. I don't know, something like that. So we're going to be looking at pretty low cut scores. But again, the actual AP exam, the written down, sit down paper one, those cut scores are similar. So I don't think it's weird.
Yeah.
Okay.
Thank you.
All right. You're welcome. I will stop the recording